Okay, so today I want to talk about the fourth postulate of quantum mechanics. So we're almost done. There's 5 postulates of quantum mechanics. There is a sixth one, but um, that one is normally not as frequently taught, and it's usually absolved within the fifth one, I think. But with that all being said, let's talk about postulate number 4 here. Well, postulate 4 roughly goes something like this. If a system is in a state that is described by a wave function, psi, then the average of the observable corresponding to A, which is an operator, operators usually have this little caret on top of them, is given by this formula right here. Now you could ask, this is really, really obscure. Why this definition? Can we prove this definition, or is this merely just a postulate that somehow just works and provides accurate results in the lab? Well, the latter of that is true, and we could just start from there. We could say, this is just a definition, and we're going to use this definition later on. But let's speed this up a little bit, because I think this is going to help us a little bit understand how to read quantum mechanics as if you're reading a book almost, because we can look at this equation and we could start remembering things that we've talked about in the past as well. And what I mean by that, and put that in the context, put this in the context of those. So I'm going to make a little table here that's going to sort of summarize everything we've talked about so far. So we're going to start off with some state phi like this. And this is a bra state. This is a state that's described by the bra basis. We know that the bra basis here is something that will take a ket basis or a ket vector, and this object that we produce is going to be part of the complex numbers. Okay. On the other hand, if we square this guy, I went over this a little bit before. We square this guy like this. Oops. With the ket like that. Then we have a real number. Because when you square complex numbers, that sort of takes the i's out of your complex number and produces a -1, which is part of the reals, right? So this here is a complex number. This here is a real number. And what I'll actually do here, let's see if I can select all this for a second and just move it over a little bit. There we go. I believe last time I called this the probability and the probability amplitude. This is actually so I don't like using terms like this because it gets, I just don't really bother to memorize the terms and the names, but this is actually probability density, right, with the square here. So I'll just say the probability density. And you'll probably hear me from every now and then refer to this as a probability amplitude. That's just me sort of forgetting the technical names of these objects. And then this here can be referred to as probability amplitude. Probability amplitude. I'll just say amplit. Okay, and then we also saw that if we sandwich an operator into here, we have something that looks like this. And we could do the same thing here. And we read this as, let me finish writing this. We read these guys as sort of what is the probability that this state is like this state. This is an inner product. Here we sort of read this as what is the probability that this operator will transform this state to become this state. Okay? So we're sort of reading this way in a sense. And then this is the probability density of that. And this is part of the complex numbers. This is part of the reals. Okay, this is the thing we actually measure. These are the things we actually measure. Okay. Now we can ask the question, what about psi and phi are two different states, but what about this guy right here? And this guy right here. Remember, A is just some arbitrary operator. What about these guys? Well, I'm going to go out on a limb and say this is part of the complex numbers. This is part of the reals. Let's prove this to ourselves, though. So we could start off with our eigenvalue question, or our eigenvalue problem. All right, so these guys here, right? I'm going to prove these. So I'm going to start off with our eigenvalue problem. Operator A acts on some state to produce state again scaled by some number. Okay. Well, if we just multiply both sides by our ket or our bra vector, we do the same thing here. We multiply both sides by our bra vector. We're just multiplying both sides by something. We could do that because just like any mathematical operation, we could do this. All right, well, A here is a number. All right, this is just a number that was multiplied by our state. So we can actually bring the number out and multiply that by the inner product between our two states. All right, well, this, again, this here is a Kronecker delta, but the two states are the same. So this is actually 1. So we end up with just A. And lo and behold, this could be a complex number. This is a complex number because fundamentally, this is a number. It could be complex or it could be real, but oftentimes in quantum mechanics, this is complex. So this could be a complex number or a real. We could say or a real number. And when we square it, we just get real, right? So this is just real. So if we were to square it, we would get this guy here A squared. And A squared, if you remember I times I times I, well, that's just -1, and that's a real number. So this is part of the reals. So we've proven, this is just a simple proof that this is actually the case. So whenever you see something like this now, whenever you see something without the square, think, okay, this is a number. This is literally just a number. This is my probability amplitude, and I can go from there. When you see the square, you think, okay, this is the thing I'm actually going to measure. This is a real number. These guys are real numbers. Okay, and hopefully this will give you like some good organizational perspective on how to read equations in quantum field theory and quantum mechanics, because again, this took me a while to sort of have this sink in. But when I realized it, it was like, these are all just numbers. Right? These literally all are just numbers. But now how about our postulate? So this is our postulate. And what's interesting, so we have our psi and psi over here. What I'm going to do now is I want to prove the postulate. Okay, this is something that is typically not done. The postulate is something that is normally just stated as the fundamental axiom of quantum mechanics, and then you go from there. But nothing's really stopping me from attempting to try to make sense of this, at least. Maybe perhaps not prove it, but we can at least make sense of it. Why is it that this is the case? All right. So I'm going to come down to this space right here, and I'm going to again start with the eigenvalue problem. Actually, no. I don't want to start with. I'm going to start actually with this. So suppose I have some operator, and I'm acting on a wave function. Well, that again. This is just I'm acting on a wave function as a ket vector. This is just going to give me another transformed ket vector, right? So what I could do is I could say, well, this is just, if I could expand this in the basis. Well, again, this is just my ket vector transformed, right? But this time I'm just expanding the basis. Okay. So I'm really not doing anything here. I'm just saying this right here is a ket vector, right? Because the operator operates on a ket vector to produce another ket vector. And I'm just going to say this is that other, I'm just right here doing the same thing. I'm just doing it for each individual basis now. Okay? So again, I can multiply both sides by my bra vector. Like this. So what do we get? We were to get something that looks like this. We would just multiply both sides by our bra vector. Operator and our ket vector. And again, this is just in the basis. There's really not that much of a difference between these two things. And we're going to infinity, or to however many we're going to. I'll just say n. However many bases we're expanding this in, for the dimensions. Okay. Well, here we're going to define this right here as that. So this here is a definition, right? We just sort of condense this notation a little bit to look like this. Now, what about this guy? This guy is discrete. If we wanted to make this guy continuous, say, for example, our psi's are continuous functions of x and t, right? Well, if we were to do that, we have to change this guy, as we all know from calculus, we have to change this guy into an integral. Okay, and we could go from negative infinity to positive infinity. And then our bra vector is our complex conjugate of our wave function. Suppose as it's a function of x and t, and this is our this is our complex conjugate. Here's our operator again. And then we just put this in its continuous form as well. That's not the complex conjugate. One more little thing we have to add to here is that we have to consider a small region that we want to, or a small interval. A small interval in some specific domain of time or space, right? But look at this. This right here is this, right? So merely by just taking a look at the transformed ket, multiplying by both sides, this is what we did here too, multiplying by both sides, merely just by multiplying by both sides, we found, and then by a raw vector of the same type, we found that the probability, or this is actually not the probability, this is actually called the average of, is it called the average? I can't really remember. This is the expectation value. So that's what it's called. This is the expectation. So the expectation value comes when these two guys are the same. And sometimes you'll see that this is the expectation value in the psi, with respect to psi state. Okay, so this is the expectation value. So this is the expectation value in psi. So what's the, so this is the of, you could say of the operator. I'll say of the operator, because I really want to put this in English, because oftentimes putting things in English, putting quantum mechanics in English does make it a degree more understandable. The expectation value of alpha, or of A, of the operator A in psi. That's how we can read this. So this is the expectation value of A in psi. Right. So what exactly is an expectation value? An expectation value is something that fundamentally quantum mechanics is probabilistic, right? This is a probabilistic mechanics. And psi could change as a function of space and time. And so if psi changes as a function of space and time, we want to consider all of those psi's within this region, within space and time. And we want to operate on sort of all of them, if you will. And from that, when we operate on all of them, we're going to get an average value from having operated on all of them. And this is what this integral does. Right, so we operate on all of the psi values between two x coordinates or two t coordinates, in this case. We want to know how they change. And then we're going to get some value, some numerical value that represents an average when you an average between the values when you operate on the states. Okay, and that's what this calculates. Right. So we're considering all of the psi's within some region of time or space. We're operating on all of them with this operator right here. And then we're getting a number out of that. Right? And so I want to actually consider something interesting here. So in GR, so now that we've talked about that, in GR, we're often almost always interested in taking vectors to real numbers, or taking covectors to real numbers, or taking combinations or combinations of the two, or tensor products of the two into real numbers. Right? So we're often interested in that kind of stuff. However, what about in quantum? So I said these guys, we have complex numbers, we're taking things to real numbers and all this kind of stuff, but what about operators? operator going to a real number? Well, if you think about this, let's think about this really quick. Let's think, what is one type of scalar that we can get from an operator? One type of scalar is the eigenvalue. So there is an eigenvalue to an operator. That's this guy right here. The other type of scalar, or another type of scalar, is the expectation value of the operator. The expectation value. And if the operator, for example, is a matrix, because matrices are operators, a determinant. So these are all numbers that are sort of attached to specific operators. They're sort of like name tags almost. It's like you have some operator here. The operator might be a matrix, right? And attached to this matrix is a couple of numbers. So we have our determinant that sort of defines the matrix for what it is. There's multiple things. We have the trace also. The trace tells it for what it is as well. Then we can have an eigenvalue that sort of goes into this little name tag. All right, my pen, there we go. And the expectation value can also go into here. And this could also be like a continuous function as well, like DDT. So although determinants and traces don't apply to the continuous operators, expectation values could. All right, so these guys are operators, and they all have these little name tags on them that have little scalars on them that tell them that sort of give us information on the nature of the operator. And the expectation value is just one of those, right? I remember a quote that I read from Pythagoras. Pythagoras was an interesting Greek philosopher, where he said that all numbers, the entire world is just a manifestation of numbers. Right? So Pythagoras was a guy who lived in ancient Greece, one of our favorite mathematicians, one of our most ancient mathematicians, and he was a fervent believer in this idea that everything that we perceive in the world is merely just a manifestation of numbers. Even operators, even these things that we can't necessarily see, they're just manifestations of just numbers, right? All these real numbers, eigenvalues, expectation values, determinants, traces, and all this kind of stuff. And so this was actually a very interesting revelation to me, this idea that operators can be represented by merely just numbers. And we pick these numbers based off of how we use the operators, right? So I want to paint an overall picture here one more time, going back to sort of my first few lectures on quantum field theory, where we have some space. Okay. And from that space, we defined it as a phase space. Okay. Same thing here. From the space, we defined it as a phase space. But, oh wait, actually, these should be the derivatives of each. But one of these is for our dual states. And so at this particular point, again, we have a couple of objects. Now, some of these objects, again, we haven't gone through in depth yet, but we have our Lagrangian We have our Hamiltonian. We have real numbers. We have our bin of real numbers and complex numbers. Then we have our operators. And we have, this is defined by our vector space, right? This is our vector space right here. And then here, everything's the same. We have Lagrangians, we have Hamiltonians. So Lagrangians, Hamiltonians, complex numbers or bin real numbers. We have operators. And then we have our vector space defined by our bra space, because our bra space, this is a map that takes us that takes ket vectors into numbers, so that when we apply these two fields together, we get numbers that we can actually measure. And what's the link? Well, if we come back down here, the expectation value, right, considers our bra space and our ket space. These aren't bras or kets, these are complex and complex conjugate, not complex conjugate. But same thing here, we have complex conjugate and not complex conjugate. So we have this little guy in the middle of these two worlds, if you will. Expectation values are extremely important. That incorporates both of these guys. Okay. So we can do stuff in this space, we could do stuff in this space, and we can link these two spaces together with our expectation value. And this is a very interesting idea that we can actually do this, right? Because we can this expectation value. Again, this expectation value is something that incorporates both of these guys together. We can operate in one space, we can operate in the other space. We can apply the two spaces together, but this expectation value fundamentally lives sort of within both spaces, because we need both of them to define our expectation value. So we have now a more complex but a more sophisticated view of these phase spaces and how they're related to one another. Phase fields, if you will. Because remember, these guys here are a function of x, y, z, and t. The space itself, this isn't x, y, z, t space like in GR. This is a phase space, right? And so that's one of the fundamental differences between the two, and that's one of the reasons it's very hard to merge the two together. But we'll see. Again, we'll see how we can attempt to marry the quantum field theory with GR. Not in this lecture, though. We still have quite a way to go, quite a ways to go to get there. I'm laying down all the preliminary work here. So we went over postulate 4. So we're coming to the end of reviewing all the postulates. And then once I am done reviewing all the postulates, then we'll get into some nitty-gritty calculations, right? We'll start to see, we'll dive deeper into the Klein-Gordon equation, the Dirac equation, the Proca equation, Lagrangians, Hamiltonians, and yeah. So I hope you guys enjoyed this, and I'll see you in the next one.